We'll get to example 7, which is pretty much a follow-up of the previous one, and then we're still gonna do the semicircle, and then we're gonna do the intensity 3 meters away from the center, but now we're gonna do the non-uniform density, right? And as I mentioned at the end of the previous example, I said that we expect this to be louder than the uniform because you are closer to the two ends, which are the louder portion of the speaker, right? So then I pretty much wrote down the result that we had from before. Remember when we did this for the rod that was straight, we calculated what the alpha needs to be. We don't have to recalculate this, so it doesn't matter the shape of the rod, as long as the density distribution is the same, as long as lambda is equal to alpha x squared, we can still use the alpha that we got, and the alpha was 50/9. So the beginning of the setup is similar again. di is dp over 4 pi r squared, lambda dx over 4 pi r squared, and then I is equal to, then the difference is that the lambda now cannot come out of the integral, so we express lambda as alpha x squared dx, and then we write down the 1 over 4 pi can come out of the integral, right? And then the r squared, we can write down the same r squared that we had before, 36 over pi squared, plus 9 plus 36 over pi, cosine of theta, right? And then the alpha can come out of the integral, right? We can bring the alpha out, but then that's all that we can bring out. X and dx we cannot bring out, right? So in the previous case, we only had a dx here. We didn't have an x squared because it was a uniform rod. So now we have this extra x squared. So we're going to have to do I is equal to alpha over 4 pi. So in where the x is, you have to put r theta, and then you have to do squared. And then where the dx is, you have to put r d theta. And then you have here 36 over pi squared plus 9 plus 36 over pi cosine theta. Right, so what's going to come out of the integral here? Well, r and then r squared, so that's going to be r cubed, right? I is equal to alpha over 4 pi. So then it's going to be r cubed is going to come out of the integral, right? And then you're going to have here theta, right? And then the limits of the integral, you can go 0 to pi over 2, and you can also double it again, right? And then when you double it, of course, you're going to get rid of the 4, okay? So you're going to have I is equal to, so it's going to be alpha over 2 pi, and then where the r is, you can put 6 over pi again. So 6 over pi quantity cubed, right? You have to cube that, and then of course multiply that by whatever the integral of this comes out. So let's integrate that. Make sure that you catch this mistake. You see here where you have the r squared, r, I put an r cubed, but theta squared, I should have put a theta squared here, right? So you need to put theta squared, and then when you put this into the integral, you can put it as x squared, and then divide it by this whole thing, and then make sure you're on radian mode again, okay? Okay, then of course I'm going to multiply that by alpha was, remember, 50/9, and then multiply that by this number squared, okay? And then now let's convert this to decibels, and then we can compare the two answers. So you can see that it is larger. The other one was 116 decibels, but it was 116 point something, but that something was closer to 1 or 2, right? And then this one is 116.88, that means it's almost 117. So almost 117 decibels, which means it is louder than the other one, but not that much louder, right? So it should be louder than the uniform, and it ended up being louder than the uniform. So now you can see how to approach it when it is uniform and when it is non-uniform, and then how to make sense of that answer, okay? Thank you very much.